Welcome to the Hidden Layer, where we decode complex AI concepts. And today, we've got a real paradox on our hands. We're going to talk about why the most advanced AI memory systems, the ones that look incredible in research papers, almost never actually work in the real world.
So you ever read some groundbreaking AI paper and think, wow, this is amazing, why aren't we using this? Well, you're not alone. Today we're digging into exactly why these super cutting-edge AI memory systems just don't make the cut in big companies. And you're going to want to stick around because by the end, I'm giving you a dead simple two-question framework that will tell you exactly which architecture to use for your next project.
I mean, you've seen it, right? Research labs are constantly pushing out these incredible, super sophisticated memory architectures. Things like hierarchical consolidation, graph-based memory, the works. But then you look at what's actually running in the real world. What do you see? Mostly it's just basic RAG, simple systems that retrieve relevant info. On paper, that seems, weaker. So what gives? What is really going on here?
And look, it's not because these big companies don't care about performance. They absolutely do. The real reason, the one that nobody talks about in the research papers, is that enterprise AI, especially in places like finance or healthcare, it has this whole hidden set of rules, requirements that most academic models just blow right past. And it all boils down to one single, incredibly important word: trust.
Okay, so what are these hidden requirements? Let's get into it. We're going to break down the four non-negotiables, the four things that an AI agent must have to even survive in a serious, high-stakes enterprise world. These aren't suggestions, they're absolute deal breakers.
All right, first up, deterministic replay. Think about it. If a regulator comes knocking and asks why a specific loan was denied 6 months ago, you better be able to rerun that exact process and get the exact same result. No exceptions. Second, auditable rationale. You need a crystal clear paper trail, from the initial input all the way to the final decision. Third is a big one, multi-tenant isolation. This means customer A's data can never, ever influence an outcome for customer B. And finally, statelessness for horizontal scale. Basically, your system needs to handle a flood of requests. We're talking thousands at once, without even breaking a sweat. And right there, that is the core of the problem. These advanced stateful memory architectures, the ones that are always updating their own internal memory, they are, by their very design, structurally incompatible with these rules. They just weren't built for this kind of environment. But there is another way, an alternative approach that was.
So why do they fail? Well, think of a stateful memory system like a really long, messy chain reaction. Every single new piece of info forces another call to an LLM just to update some internal summary. Every one of those calls adds risk, a little bit of randomness, and it's another thing an auditor has to dig through. A stateless architecture, it just sidesteps that whole mess. It's one single, clean, pure function call right when you need the decision. Simple. Auditable.
Okay, so if stateful memory is out, what do we do? How do we get that awesome performance we see in the research papers, but without all the risk? This is where we get to the solution, and it's a really elegant one from the paper we're looking at. It's called Deterministic Projection Memory, or DPM for short. The core idea here is actually super simple, but really powerful. It's inspired by stuff like financial ledgers. So instead of constantly summarizing and re-summarizing, you just treat the agent's entire experience, every document it sees, every message it gets, every tool it uses, as a permanent, unchangeable log of events. It's an append-only log. Nothing gets edited, nothing gets condensed, not yet. So here's how it works. It's just 2 steps. Step 1, as the agent does its thing, you just log everything. You're just creating this append-only event log. That becomes your single source of truth. Then, step 2, and this is the key part, only at the very moment you need a decision, then you make one single call to your LLM. It reads that entire log from start to finish and projects a clean, structured memory view from it. And that's it. 2 steps. So right away, you can see this approach is clean, it's auditable, it's stateless. It checks all the enterprise boxes. But I know what you're thinking. As an engineer, the real question is, does it work? Is the performance any good? Let's dive into the data from the study and see how DPM really stacks up against the old stateful way. Okay, now this is where it gets really interesting. This is the part that matters. Look, when you have a generous memory budget, all the tokens you want, both approaches perform about the same. It's a wash. But now, look at the tight budget scenario. This is what the real world looks like, right? Production is always about constraints. And here, DPM just crushes it. It massively outperforms on factual precision, on reasoning. Why? Because it hasn't accidentally dropped critical details in some long, lossy chain of summaries.
And get this, it's not just better, it's way faster. And cheaper. We're talking 7 to 15 times faster. Why? Because DPM makes just one big LLM call at the very end, instead of potentially dozens or even hundreds of little calls all along the way. Think about that. For a system making thousands of decisions an hour, that's a huge operational saving.
This chart really tells the whole story. It's super clear. That bottom axis, the x-axis, that's the compression ratio, basically how much you have to squeeze the agent's memory. And as you move to the right, as that budget gets tighter and tighter, the performance gap just gets wider. The stateful approach starts bleeding information, it starts forgetting critical facts. But DPM, because it makes that one final projection, it can still see the whole picture. Its advantage just keeps growing.
All right, let's bring this all home. I promised you at the start that we'd get to a practical way to apply all this, so let's get to it. This is the decision-making framework from the paper, and it's called the TAMS heuristic.
Okay, listen up. Because for you, the applied engineer who's actually out there building these systems, this is probably the most important slide in the whole deck. This is a dead simple set of rules to guide your next architecture choice. It's designed to cut right through all the hype and all the noise.
So here it is, the TAMS heuristic. Think of it like a two-question flowchart. Question 1, does your system need those enterprise-grade trust properties we talked about? Determinism, auditability, isolation? If the answer is yes, stop right there. Use DPM. End of story. Okay, but what if the answer is no? Then you go to question 2. Is your memory budget tight? Is that compression ratio going to be more than, say, 10 to 1? If the answer is yes, then you should use DPM for the performance boost. And if you answer no to both questions, well, then you're in a great spot and either architecture is probably fine. It's really that simple.
And this isn't just some abstract academic exercise, right? For you, this means you can build agents that are actually verifiable and auditable. Your compliance team is going to love you for that. It means you're going to reduce your operational costs and make your life simpler. And maybe most importantly, it means building AI systems that are way more reliable and actually work in production. We're finally closing that gap between the cool stuff in the papers and what delivers real-world value.
And that's really the big takeaway from all this research. For years, it felt like you had to make a choice. You could have a smart agent that was basically a black box, or a trustworthy agent that was kind of dumb. What this shows is that that's a false choice. With an architecture like DPM, you can finally have both. So I'm going to leave you with one final thought to take back with you. Now that you know it's possible to build AI agents that are both incredibly powerful and totally trustworthy, how is that going to change the way you design your next project? What can you build now that you couldn't before? Thanks for watching The Hidden Layer.